All right, hey everybody. I wanted to dive a little bit deeper into these stress results. So, if we go back to our hand calc for load case one, you'll see that even though I loaded it apart in the y direction, we're getting a tensile stress, a normal x tensile stress. And when I first looked at that, I was kind of curious. Um, and I had to look through those results a little bit more carefully. And for our first load case, if we look at the normal stress in the x direction, uh, and actually let me do this. I'm going to plot the normal stress for the whole part in the x direction. Okay, so I've set up here. I have in the results. I've gone and you can go up here and you can look at the undeformed model. And for this case, I am looking at a 5x of the scale factor. And I'm also showing the undeformed part. So I've created a plot where they're overlaid, and this is really helpful in interpreting part deformation and interpreting your stresses. Um, so in order to get the part, this plot to have your both your deformed and your deformed shape, so you can go here to edges and you can click show undeformed model. You can also click show undeformed wireframe model. There that. So the reason why we have a normal stress in the x direction is because we fixed the bottom, and when you pull the part in the y direction, it it's going to there's going to be a strain in the vertical direction, and then the part is going to want to contract. So because the part wants to contract inwards and it's constrained, there'll be a tensile stress. And the way I like to think about it is in relation to thermal stresses. So if you constrain a bar on two ends and you heated it up, the bar is gonna would want to expand, and there'd be a compressive stress. And then likewise, if you um, cooled the bar and fixed it at two ends, it would want to contract, and there would be a tensile stress. So in this case, the bar wants to contract and it can't. So there's a tensile stress uh, in the X component. And that's why we see that show up here for our part. Now, the other aspect that I thought was curious when I loaded this um, for the second load case is I loaded it along the right face here in the X direction, and it's fixed at the bottom. So we'll get a bending stress, a moment reaction in the bottom, and there'll be a shear stress. But what I found was curious is at the center of the part, in the this would be the neutral axis of the part if it was in bending, is that we actually got a compressive stress in the y in the normal y direction, and I would have thought that this would have been zero because there's no bending there, and we do have a shear stress, which makes sense. And so what I did is I created the path. Again, I'm going to show how to do this in a separate video through the part. And I plotted the results on that path. I did a linearized normal stress in the y direction. And you see here, if you go over to the calculation that ANSYS does, you see here there's almost no membrane stress, very small, and it's all bending. And the bending stress does go to zero at the neutral axis. So this would be the path would go to 0.5 inches, which would be in the where the neutral axis is. But we have this stress, and again, so I went through this and actually calculated it. And again, that's related to the fact that we fixed the bottom, and there's some the part wants to contract and it can't. So I actually pulled the strain from the model, and I went through the Poisson's calculation, and I got this stress result. So we're seeing a slight compressive stress because of the way that the part wants to contract from the loading, and it's fixed. And I also looked at the shear stress through the part. And if you remember from your shear stress calc, you can actually calculate this shear stress. And this is what the um, profile would look like if you did it by hand. And you see that there's a maximum shear in the center, and then it goes to zero at the top and bottom of the beam. So yeah, I wanted to add that just in case you, the viewer, were questioning why those stresses were what they were. And again, that's why it's important to go through these results and really make sure they make sense by hand if you're comparing them to hand calcs, just to make sure that you're validating how you loaded your FEA model and you validate your boundary conditions, and you get the the results that line up with theory. But yeah, thanks for watching. Hopefully you guys learned something, and looking forward to making some more videos.